Welcome to chemistry at Hononegah High School. Today we'll be looking at our last section of ideas from 4.3 in chapter 4, where we'll be looking at the idea of average atomic mass and how it's calculated. Because the mass of atoms is so small, remember proton, very small object, 1.67 times 10 to the negative 24th grams, we simplify atomic masses by measuring them in what we call atomic mass units. Now, an atomic mass unit, or an AMU, sometimes also written U, is equal to 1/12 the mass of a carbon-12 atom. So with what we talked about with isotopes, carbon-12 atom, carbon has atomic number 6, so 6 protons, 6 neutrons, and a total of 6 electrons. So if you take, remember the electron, significantly smaller in mass, typical carbon-12 atom, we chop that into one piece, we're looking at basically the proton or the neutron. So when we look at actual atomic masses and atomic mass units of substances, something like hydrogen 1 equals 1.007825 AMUs, whereas silicon-30, 29.974 AMUs. You'll notice there is a close relationship here between what our mass number was and what the mass in atomic mass units is, especially if we look at it to the tenths here. So hydrogen 1, 1.0. Silicon-30, 29.97. Well, if we look at it to the 10th, that's 30.0. So one of the reasons why the mass number is called the mass number, even though it adds to confusion with mass number and atomic mass, and students sometimes think they can look at the periodic table to get the mass number, when what they're looking at is the average atomic mass. One of the reasons why it's called the mass number is because it's the approximate mass of the isotope in atomic mass units to the tenths. Now, if elements have isotopes with different atomic masses, then what's the atomic mass on the periodic table? I've already given this away a couple of times in class as well as in this notes, because what we really are looking at on the periodic table is it's the average atomic mass. It's a weighted average of the mass of the isotopes of an element. Now, this is a little bit different than like the average amount of money. If we found out, what is the average amount of money of a person in our classroom right now? That can change from day to day to day, depending on how much money you happen to have on you. Well, it's different when we're looking at isotopes of elements, because when we're looking at the stable isotopes of a given element, the percentages or the amounts of each type of isotope in a sample is always going to be set. So unlike, the percent number of females in the room versus the number of males, or the average amount of money that we have. I mean, those things can change from day to day as people move in and out of the room, and we exchange males for females and so forth. But with average atomic mass, when we're looking at a large sample of any substance, and remember, atoms are so incredibly small, even a very small sample size on what we would say is small, it's still an inconceivably huge number. So what we look at for average atomic masses is the fact that the percent abundances, as they're called, what percent is this isotope, what percent is that isotope, that amount is set no matter where we get our sample from around the planet or around the universe. And we actually find average then very differently than we normally do, because we can't count all of the atoms, weigh them, and then find out the total weight. We can't do that with atoms because they're so small. So what we do is we use a different averaging technique that fundamentally gives us the exact same information. So what we do is we sum the mass contribution of each isotope in the element. So basically what's happening is every particular particle contributes to the average, and its mass contribution is how much that particular isotope is contributing to the overall average. And then we add all those mass contributions up. So what really is a mass contribution, and how do we find it? Well, it's the mass of the isotope times the decimal form of the abundance. Remember, when we have a percent, we've artificially multiplied it by 100 to make the number more normal and meaningful and understandable to everybody around us. We've dummied it down. People understand 97% much better than they understand what 0.97 per 1 would equal. So we have to get rid of that artificial multiplying by 100. So we take our percent and convert it back to a decimal. And then we multiply that times the mass. So we're literally taking that percent of the mass. And that's really what the mass contribution is. The mass contribution is that component right there. The mass of the isotope times its percent abundance back as a decimal. So let's make it simpler. Let's break it down and look at exactly what we're doing here. So each substance is going to contribute to the overall average. Like if you have money and we calculate the average amount of money in this room, everybody is actually contributing to what the average is. What we really need to do is find out how much they contribute. So how much it contributes is based upon its percent abundance. So let's keep it simple. Let's say in this room, most of the people, 90% of you had $1, 10% of you had $10. Well, the people that had $1 are going to contribute more to the average because 90% of the people contributing to the average only had $1. So the more you have, the more it affects or contributes to the average. So let's really simple numbers, really simple ideas here. 60% of a sample weighs 12 and 40% of the sample weighs 14. So I have an isotope, or I should say I have an element with two isotopes. The element that weighs 12 atomic mass units, 60% of any sample is going to be that isotope, and 40% of any sample is going to be the isotope that weighs 14. So this means that 60% of our average is going to be caused by the mass or by the isotope that weighed 12. Now what we're really just doing here is taking 60% of 12 to find its mass contribution. So what that would look like in a problem, well 60% of our element weighs 12 AMUs. So 60% of 12 is 12 AMUs times 60 over 100. Remember, we need to change that 60 back to a decimal. So what we're really doing is what I've showed down here in the bottom. And that's where that comes from. So convert your percent back to a decimal, and then you're multiplying it by your mass. Now, the next thing you do is you literally plug that in your calculator. So what does 12 times 0.6 equal? And that's what you're going to record as your calculator answer. But remember, and we just got done practicing this for an entire chapter, and this is never going to go away. Every time we do a calculation, we have to evaluate that calculation to report our answer as precisely and as correctly as possible. So we have to take a look at significant digits is really what it comes down to. And in this particular case, 60% is a terrible measurement. It only has one significant digit. So 7.2 AMUs would have to be written as 7 AMUs would be our rounded answer. Now remember, when we're multiplying or dividing, it's about how many sig figs you round to the least significant number. When you're adding or subtracting, it's about the uncertainty. You round your answer to the biggest uncertainty, both of which actually happen in this type of problem, which we'll see in a second. So here's an actual problem. There are two naturally occurring isotopes of copper, copper-63 and copper-65. If copper-63 has a mass of 62.930 AMU and 90 or 69.1% abundance, and copper-65 has a mass of 64.928 AMU and a 30.83% abundance, what's the average atomic mass of copper? Now, first we're going to calculate the mass contribution of each isotope, and you need to basically watch your sig figs when you do that. So being sure to convert each percent to a fraction abundance, so that means divide by 100. You're going to get your calculator answer, and then we're going to get a rounded answer. And remember, what we're finding is our mass contribution, the mass of the isotope times the abundance of the isotope as a decimal. So in the case of this problem, if we look at our table down at the bottom, which we're going to use consistently with these type of things, so we organize our information in a way that makes sense. First, we're going to look at the mass contribution of copper-63. So its mass, 62.930 AMU, times its percent abundance as a decimal. 69.17 divided by 100, move the decimal 2 to the left, you get 0.6917. So that would be what we put in our work spot here, our first step. Now, next you put it in the calculator, see what you get. So to a whole bunch of sig figs, this is what the calculator gives me. But next I need to evaluate that answer and get the right rounded answer. 62.930 has 5 sig figs. 0.6917 has 4. 4 is less significant than 5, so we can only round our, or we have to round our answer to 4 sig figs. So we count over 4 places, which means we're rounding at the 2 in the hundredth spot right here. Next digit's a 8, so we're going to round up to 43.53 AMU. Now we're going to turn around and calculate then the mass contribution of the copper-64. Find it the exact same way. Take its mass times its abundance as a decimal. Plug it into the calculator, see what the calculator gives us, and then evaluate and round. Once again, 5 sig figs, 4 sig figs, we're going to have to round to 4. So in this particular case, we're rounding at the 1. Next digit is 7, so I'm going to round up to 20.02 AMU. Now, I now have calculated the mass contribution of each isotope. Notice copper-63 is contributing more to the average. Well, that makes sense. 69.1% of our sample weighed copper, or was copper 63, which weighed around 63. So in this particular case, you can see the more abundant substance is contributing more to the average. Now, to find out what that average is, all we need to do is sum it together. Now, when you add or subtract, remember you're looking at uncertainties. This one's uncertain here. That means it's the last significant digit. This one's last significant digit is there. They're both in the hundred spot, so that's where I need to round the hundreds. Well, that's exactly what the calculator is going to give me. It's already going to give me an answer to the hundredths. So 63.55, the calculator answer is the right rounded answer in this case. So that's how we calculate average atomic masses. Now, let's look at one more problem with a slightly different emphasis in it. So in this particular case, notice we don't know what the element is. The last one we knew was copper, so we got our final answer, 63.55. We could look it up and compare to what's on the table to get an idea if we got the right answer or not. And so in this case, we don't want to know what it is. That's going to be part of our job. We just know it's element X. It has two naturally occurring isotopes. An isotope that we're going to mark as X6 that weighs 6.05 or 0.015 atomic mass units with a percent abundance of 7.50. And the other isotope weighs 7.016, and it has a relative abundance of a whopping 92.50%. So that tells me my final average should be closer to 7 than to 6, because 92.5%, that substance, that isotope, is going to contribute significantly more to the average. So set up a problem, we do the same thing. We find the mass contribution of the X6, so that would be percent back as a decimal, so divide by 100. Get your calculator answer, and in this case, we've got 3 sig figs in 7 or 0.0750 and 4 sig figs for 6.015. We're going to round to 3, which means we're going to round at that one right there, and we end up with 0.451 AMU. Now we turn around and find the mass contribution of X7. Its mass times its percent as a decimal, divide by 100, so 0.9250. Plug it into the calculator, and then remember, we have to do the same thing. Even though that's the calculator answer, that might not be the right rounded answer. This one has 4 sig figs. That one has 4. I'm going to round to 4. So I'm rounding, oops, nope, that's only 3 sig figs. Looks like I need to round to the thousandths place where the 9 is. Well, the next digit is an 8, so I'm going to round up. And think of it as 89 rounding up to 90. So we've got 6.490, and yes, we need to have that 0 there because it should be uncertain to 3 decimal places. So it should be uncertain to the thousandths, and that's exactly where it is. So those would be the amounts that each one is contributing to the overall average. To finish it up, you just combine and round. Well, both of these are uncertain to the 3rd decimal place, so my calculator gives me the 3rd decimal place. That would be the right rounded answer, 6.941 AMU. Now, the last thing that we can look at here is we didn't know what the substance was, but now we've calculated its average atomic mass. Now, if this data was real data based on a real elemental substance, we should be able to take a look at the periodic table and see if we can find anything that weighs about 6.941. And when you do that, what was our mystery element? The only one even remotely close, and lithium is very, very, very close, is lithium. So in this particular case, we actually used it to find out what the unknown substance was. And you should be prepared to do that in a question for the test. And that ends our Chapter 4